delta H varies with conditions, so delta H values are taken in so-called standard states so as to be able to compare them as thermodynamic data. And it's pretty simple. For a gas, the standard state is 1 atmosphere. For a solution, the standard state is a 1 molar concentration. Nothing too surprising there. 1 molar means 1 mole per liter. For an element or a compound, the standard state is the most stable form of that element at 1 atmosphere, and the temperature is usually 25 degrees or 298 Kelvin. Sometimes there's some other, depending on the compound. If it's an explosive compound that blows up at 25 degrees, you probably would want to study it at a lower temperature. So it may be necessary to have a different temperature. And if you take some physical chemistry later on in your career at the U of H, you'll hear more about that. So delta H's of reaction, measured with all the substances in their standard states, are given a special name. They're called standard reactions, and their heat is the standard heat of reaction, and it's given the symbol delta H naught, that little zero that looks like a degree Celsius sign. That means standard state. Okay, there it is. You see the red circle around it. And so delta H naught of reaction is the delta H for a reaction carried out with the substances in their standard state. Okay, now formation reactions are usually cited under standard conditions. So that's the reason I talked about standard conditions first. The formation reaction for some compound constitutes 1 mole of the compound being formed from its elements. Draw 2 lines under formation, because I want you to remember that. If any question talks about the formation reaction or the formation of some compound, you can write the equation for the formation by taking the compound's formula and writing down the elements in the right numbers, and then just drawing a line and saying they produce this product. Doesn't mean the reaction occurs. They usually don't, but that doesn't matter. Thermodynamics only is worried about where we started and where we finished, not about how we got there. So if we looked at the formation equation for the formation reaction of sodium chloride solid, we look at the formula, and it says if I'm going to make 1 mole of sodium chloride solid, I'm going to use 1 mole of sodium. In its elemental form, it's a solid. So NaS, meaning solid or crystalline. And I need 1 mole of chlorine, so chlorine is one of the famous 7 diatomics. It's going to come as Cl2 under standard conditions, so it's going to take 1/2 of dichlorine to make NaCl. So that's the formation reaction for NaCl. And we'll do some of these so you'll be comfortable with it, but you just start with the formula, pick out the elements, and write them down. The delta H of formation of sodium chloride is the delta H of the reaction in the formation reaction, I should say, with the substances in their standard state. So the delta H of this reaction, as I have written it, has a special symbol. Delta H naught. Naught means standard conditions. F means formation. Okay? Draw a circle around the F so you'll remember that it's for the formation reaction. Okay, so let's look at methane. Methane is CH4, so that means the formation reaction is going to start with carbon in the standard state, which is graphite, 1 mole of that, plus hydrogen in the standard state, which is H2 gas, 2 moles. So if we write the formation equation, it's carbon graphite plus 2H2 gas goes to CH4 gas. The delta H for that is the delta H of formation of methane. And if it's done under standard conditions, we'll put the naught in there, and we'll put the F here to indicate that it is the formation, delta H of formation. Okay, so that's the relationship between delta H of formation and delta H of reaction. You have to have the right reaction. Questions on that? All right, good. Notice this is negative. Most delta H's of formation are negative for stable compounds. All that really means, if you think about it, is the compound is more stable than its parent elements. Forming the compound is sort of downhill energy-wise. Okay, that's all right. During the next 3 weeks, you'll have to look up some delta H's of formation. I'm going to show you why in a minute. And the best place to find them is either in Table 6.3 of your textbook, or if you need one that isn't there, and you might, there is an appendix about properties of compounds, and it also gives delta H's of formation. So an element in its standard state has a delta H of formation of 0. That's the baseline, if you will. It's defined that way. And so I put this in a tinted form so that you'll remember. Any element in its standard state has a delta H of formation of 0. Okay? And as I said, most compounds have negative delta H's of formation, and that's the reason. Okay. Now, what I have here is a problem. We need to write the formation equations for 1 mole of each one of these compounds from their elements. And the delta H, the silver chloride here, has a formation reaction then of silver plus 1/2 Cl2 goes to AgCl. So silver, 1 mole, 1/2 Cl2 goes to AgCl. And when I go look up the heat of formation of AgCl, table 6.3, it's negative 127.0 kilojoules. So this is the equation. This is the enthalpy of formation for AgCl. For calcium carbonate, it's 1 calcium, 1 mole of calcium, 1 mole of graphite, plus 3/2 mole of dioxygen. And this gives CaCO3. And the reason for the coefficients of 1, 1, and 3/2 are that's the ratio of the elements in the formula. And when I look this value up, it's negative 1206.9 kilojoules. Finally, hydrogen cyanide, if you look at that, you know it's going to be H2 plus C plus N2, half an H2, 1 C, and half an N2 to form HCN. Here it is, 1/2 H2 gas plus C graphite plus 1/2 N2 gas goes to 2 HCN. And if you look at that, it's plus 135 kilojoules. That usually means when you see a delta H of a compound that's a positive number, particularly one this big, it means it's very unstable, maybe highly reactive. And of course, HCN that's true for HCN in every way imaginable. It's highly toxic. Okay, now the last thing I want to talk about from the perspective of delta H's reaction is how to use delta H of formation values, if you're given those in a problem, to calculate the delta H of reaction. And it works like this. Let's imagine that we have an enthalpy diagram here, and we have a reaction, and these are the reactants. And from that reaction, when we carry it out, we get these products, and the products are down here at a lower enthalpy value. So the delta H for this reaction, carried out under standard conditions, is the length of this yellow arrow. Now, if we measured this reaction in a calorimeter, the Q for this process, from which we would get the delta H, is the length of this arrow. Okay? But let's suppose we don't want to do this in a calorimeter, and we would like to have an alternate way to get the delta H reaction. The alternate way uses, that I'm going to show you now, uses delta H's of formation. Now let's suppose we take the reactants and we break them down to their elements. All the reactants are broken down to their elements. By the definition of delta H of formation, this is the reverse of the formation reaction. Instead of going from elements forming the compounds, we're going from the compounds to the component elements. So for each one of these, the length of the arrow for it is minus delta H of formation. Minus because we're decomposing the reactant rather than forming the reactant. So the standard enthalpy change for each reactant is minus delta H of its formation. The minus is because we're breaking it down. If we take those elements now, we can imagine, this is strictly a formalism, something in our head that we work out. Well, Hess worked it out. We'll have to thank him for that. Or maybe you won't thank him. I don't know. Elements going to the products, the delta H for each one of them is the delta H of formation of that product. It's elements going to products, so it meets the definition. And now what I want to show you is the delta H of reaction here is equal to the difference in length between these two arrows. So we're going to write an equation for this. The delta H of reaction is the sum of the delta H of products minus, that's this line right here, minus the sum of the delta H of formation for the reactants. So all we need is delta H of formation values and a balanced chemical equation, and we could calculate delta H. Okay? So here it is written out for you. Delta H reaction is the summation of the coefficients for each product times the delta H of formation for that product, minus the summation of the coefficient, n is the coefficient for reactants, times the delta H of formation of the reactants. And it works like this. M and N are the coefficients, so we need them in the actual calculation. We are going to consider the following reaction. Back in the 70s, when there was a significant gasoline shortage, the Army considered running its tanks using ammonia. Ammonia and oxygen will combine to make NO and water, and the question is, how much heat should we expect to get from that? And we can find that out using this equation and delta H values. Now I'm going to write down the delta H values here. I have them. The delta H of formation for ammonia, one mole of ammonia is plus 49 kilojoules. These are all in kilojoules. Oxygen is the elemental form, so what's its delta H of formation? 0. Good. Good. One person got it. Anyhow. Elements, delta H of formation, 0. NO, if I go and look that up in table 6.3, it's negative. I'm busily looking at the wrong, here it is. I looked at the wrong page. Would you please make this correction right here? Instead of minus plus 49, this is minus 45.9. 0 is right, and NO is plus 90.3 kilojoules, and water gas is negative 241.8 kilojoules. They're all in kilojoules. So I have what I need to plug in, and this is the equation. Delta H of reaction is 4 times the delta H of formation of NO, which is plus 90, plus 6 times the delta H of formation of water in the gaseous form, which is negative 241.8, minus 4 times the delta H of formation of ammonia, right here, plus 5 times the delta H of formation of oxygen, which is 0. We put in the numbers, 4 times 90.3 plus 6 times negative 241.8 minus 4 times 45.9 plus 5 times 0, and the number comes out, minus 906 kilojoules. Remember, not kilojoules per mole. This is a delta H of reaction that we just used delta H's of formation to calculate. So, the gist of that particular story is that tanks ran just fine on ammonia, but when the NO came in contact with air and water, it made nitric acid. And unfortunately, the nitric acid did horrible things to the engines of the tanks. So that was eventually given up, and the Army I'm sure, decided it might be good to hire a chemist once in a while. Question? Okay. Let's have a look at this last example out of Chapter 6. Calculate the delta H of combustion of benzene, C6H6, given that the delta H of formation of benzene is plus 49 and the delta H of formation of carbon dioxide gas is negative 393.5. The delta H of formation of liquid water is negative 285.9. Okay? Now, this is the third way that we had for determining delta H of a reaction. This is a combustion reaction, so you need to remember how this one works because it's a plug and chug type. So delta H of reaction in this kind of a case is equal to the summation of M times the delta H of formation of the products minus the summation of N times the delta H of formation, this is formation here, of the reactants. Now, in order to know what the products and reactants are, of course, we're going to have a balanced chemical equation. And we're going to have to know what combustion is and what the products are, combustion. So the combustion of benzene, which happens when you drive your car, goes like this. 1 mole of benzene plus 15 halves moles of oxygen gas goes to 6 CO2 gas plus 3 H2O liquid. So the products are CO2 and liquid water. The reactants are benzene and oxygen. So the delta H of reaction, which will be equal to the delta H of combustion, because this is a combustion reaction. COMB is not comb, it is combustion. So this is equal to 6 times the delta H of formation of CO2 gas plus 3 times the delta H of formation of H2O liquid minus, I'll put this in brackets and put the whole thing in there, minus the delta H of formation of benzene plus the delta H of formation of, I'm sorry, this is 15 halves, the delta H of formation of dioxygen gas. And of course you know that since this is the elemental form of oxygen, this term is 0. The delta H of formation of all substances that are elements and they're in their elemental state, 0. We learned that last time. So from here on it becomes a plug and chug. 6 moles of CO2 times negative 393.5 kilojoules per mole plus 3 moles of H2O times negative 285.9 kilojoules per mole minus 1 mole times 49.0 kilojoules of benzene per mole. And if we plug in the numbers, the moles all cancel. Our answer will be in kilojoules. The intermediate answer is negative 2361 for the CO2, negative 858 kilojoules for the water, negative 49 kilojoules for the benzene, and if I did my arithmetic right, which is 50-50 chance, negative 3,268 kilojoules. Not kilojoules per mole. And that's delta H reaction, and that's exactly equal to delta H of combustion.